Hello everyone, my name is Ray Chen. I'll be talking about our paper, Safe Interactive Industrial Robots Using Jerk-Based SafeSet Algorithm. First, let's talk about our motivation and problem setting. Currently, most industrial robots are used in highly controlled environments. Cells and fans are used to separate robots from human for safety. In some tasks where human must be present, it is desirable that robots work in proximity with them to provide necessary help and improve efficiency. One challenge here is the safety of human. When both robot and human are in motion, safety hazards such as collisions might happen. It is desirable that robots can actively avoid collision with the humans without coming to a complete stop, and continue to perform the task whenever it is safe to do so. Then, let's talk about some challenges. We identify two main challenges in this task. First, the robot needs to react to obstacles in real time, meaning that it needs to be able to replace its tracking reference even when the current reference is not finished. Second, we need to guarantee that the robot motion is always safe, meaning that we need to perturb the task-specific nominal control whenever necessary. In this paper, we focus on the second challenge, since the first one has been resolved by our prior work. To be more specific, let's continue the discussion within the context of a widely used industrial robot, Fanuc LR-Mate 200. It accepts high-frequency position control trajectories with bounded jerk. Our prior work, the jerk-bounded position controller with real-time task modification, provides the capability of online trajectory replacement, hence we are able to modify the tracking reference even when the current one is not finished. In this work, we continue to tackle the challenge of robot motion safety by developing a safe control for robotic systems. In our prior work, we have addressed the safe control for acceleration-based systems. In this work, we address safe control for jerk-based systems. We developed jerk-based safe control to enforce the jerk bound, hence our work is applicable to any robot arm with similar constraints. Then let's talk about our method of safe control. In our problem, we assume that a nominal controller generates jerk control sequences U to perform user-specific tasks. The safe controller, on the other hand, will perturb the nominal control if necessary to guarantee safety. Considering an unjoined robot, we represent the robot state as a vector Q containing the position, velocity, and acceleration of each joint. Then, we model the robot dynamics as a third-order integrator where the control input is a joint jerk. The control input is also bounded depending on the actual robot. Now, since we are interested in avoiding collision between the robot and obstacles, we also model the environment. To simplify the computation, we represent the geometry of both the robot and obstacles using capsules. In human-robot interaction case, we denote the capsules of the robot and the human as CR and CH respectively. Then we need to ensure that the distance between CR and CH is always above some threshold d mean. In more general cases, we categorize the obstacles into two types: static obstacles, whose states are constant, and dynamic obstacles, which we assume to have constant acceleration, such as humans. This is a realistic assumption since the human motions are normally smooth. Finally, we represent the full environment state as a union of the static and dynamic obstacles. Now, the whole system state is just a concatenation of both the robot state Q and the environment state E. We can then design our safety criteria. We choose to represent the safe set XS as a zero sublevel set of a real valued function phi0. Phi0 should be designed according to the task. In the previous example, phi0 can be assigned to be d mean minus d, meaning that we want the distance between the robot and obstacles to be over d mean. The goal of safe control is then to modify nominal control UK such that the system state will always stay inside the safe set XS. This property is called the forward invariance. It is not obvious how the forward invariance can be achieved. Luckily, our prior work provides a principal way to design the safe controller to achieve forward invariance. The theorem basically says that as long as we can synthesize a safety index phi and enforce a constraint of phi less or equal than 0 throughout the control, the forward invariance is guaranteed. Specifically, phi should be written as the linear combination of the function phi0 star and different derivatives of phi0. The function phi0 star can be any function that has the same zero sublevel set as phi0, and it is introduced to non-linearly shape the boundary of the forward invariant set. For other conditions that should be met, please see our paper. Under the previous theorem, we proposed a safe control algorithm for third-order system, the jerk-based safe set algorithm, or JSSA for short. The safety index is the linear combination of phi0 star and the first and second order derivatives of phi0. Setting the safety criteria to enforce minimum robot obstacle distance, we arrive at the final control law as a constraint optimization problem. Note that the constraint here can actually be simplified into a linear form with respect to the control. Hence, the problem is actually a QP and can be efficiently solved. To summarize our contribution, this work applies to third-order systems, while prior work applies to second-order systems. We also successfully applied this work into an industrial robot with real-time position control loop. Now, let's visualize how safety is guaranteed. The figure to the right is a 3D plot with the axis being the phi0 and its derivatives. We plot the safety criteria as phi0 less or equal than 0, bounded by the transparent plane. Any state beyond this plane is considered unsafe. We also plot the surface of phi equals 0 representing the safety constraint. The shaded volume here is a forward invariant safe set, and it's a subset of phi0 less or equal than 0, or XS. Whenever the state approaches phi equals 0, the safety control law will perturb the nominal control to drive the state back to safety. Also, it can be proved that the state will never cross the plane of phi 0 equals 0 even when phi is less than 0. Hence, under this control law, the system will never go out of the safe set which complies with the safety criteria, and the system is always safe. Then, let's talk about how we implement our algorithm on the hardware. We're using a phonic robot with string motion interface. The robot accepts position control trajectories in 125 Hz and communication at 1 kHz for stability. To create a stable 1 kHz control loop, we implement both nominal controller and GSSA on a real-time target machine. The host machine processes the task and sends tracking queries to the target machine. Then the target machine would invoke the nominal and safe controller to drive the robot. Finally, let's look at some results. First, we perform a sensitivity analysis on the hyperparameter of our safety index. To make fair comparisons, we simulate a human motion and use the same test case for all different parameter settings. In the simulation, the human approaches the robot, stops, and moves away. The robot is expected to avoid human and guarantee safety during this process. We evaluate the performance of GSSA in terms of 6 metrics. The first one is minimal relative distance between the human and robot, which is directly related to the safety criteria. The second one is the first and last trigger time of GSSA, and we compute the duration of GSSA active time. Finally, we compute the average critical velocity and acceleration between the human and robot to see whether the interaction is smooth. We summarize our results in the following table. We test 3 choices of lambda 1 and lambda 2 respectively, resulting in 9 parameter settings. We report all 6 matrices in the parentheses. First, let's look at the effect of changing lambda 1. We observe that when lambda 1 increases, the minimal distance between the human and robot increases as well, and the JSSA is active for a longer time. That means that lambda 1 would make the system more conservative as long as the robot's obstacle distance is shrinking, as can be seen in this animation. Now, when lambda 2 is increasing, the minimal robot obstacle distance actually decreases. This is because although the human is approaching the robot, the human is decelerating, resulting in the relative acceleration pointing away from the robot. This indicates a decrease in risk level, and hence the GSSA is less likely to be triggered with a larger lambda 2. Also, we observe that the relative acceleration is lower. This means that a larger lambda 2 will make the system's motion smoother. We also demonstrate the GSSA in a real-time human-robot handover task. In this task, the human would suddenly approach the robot when the robot is passing a power tool. The robot is expected to take a detour and avoid potential collision, and only proceed when it's safe. We plot the robot profiles during this task on the right. We can see from the top figure that the minimal human-robot distance is always above the threshold, which is drawn by the red dashed line. The second and third figures show that the robot is always trying to reach the desired location without going to a complete stop. The figure at the bottom shows when the GSSA is triggered, and these spikes correspond to the moments when the robot starts to deviate from the nominal tracking references. Finally, we have some future work. First, we currently only consider the collision avoidance between the robot and the closest obstacle in the environment. We aim to consider multiple obstacles as future work. Second, we assume that a control always exists for the safe control law. However, that is highly dependent on the choices of hyperparameters. We will develop a principal way to assign those values. Finally, it will be worth studying the characterization of the forward invariant set associated with our safe control law, such that we can optimize the safety index for task efficiency in an informed way. Thank you.